Okay, so welcome to this video in which we're going to explore three bigger ideas in similarity and proportion. Right, we're going to start off by just understanding what we mean by proportion. Those two fish are in the same proportion. For example, if we've got the dimensions of A and C for the tail and the length respectively, and if we've got the same corresponding figures on the bigger fish of B and D for the tail and the length, then if we take a piece from the small fish and we divide by another piece from the small fish, we must get exactly the same answer as if we divide the corresponding lengths from the big fish, so D over B. Alternatively, we could take a length from the small fish, some sort of dimension from the small fish, so the tail from the small fish divided by the tail from the big fish, and that must give us exactly the same answer as the length from the big fish divided by the length from the small fish divided by the length from the big fish. Right, these fish are not in proportion. They will not give the same ratios if we divide corresponding lengths. So three big ideas and then a strategy, and then really after that it's just all about practice. The first idea is that these two triangles share a height. Now that might not be immediately obvious to you, but what will make it simpler is if we just turn that diagram. So let's have a look, and you obviously can turn your book around. So at the moment it's not at all obvious what they share. However, if we turn the diagram around, then it becomes more obvious that in fact they share a perpendicular height, and we could draw that height in. It would go somewhere around there, perpendicular to the base. If we now look at the ratio of the area of the blue triangle to the red triangle, having turned it round with the base as AD, then the area would be half AD times that height that we drew in just now, and the area of the red triangle would half DC times that height. The halves and the heights divide out, leaving us just with AD over DC. We could also look at, for example, the whole triangle, the big triangle, as to the red triangle. So the area of the whole triangle divided by the area of the red triangle. Well, the whole triangle would be the half the base of AC times the height. The area of the red triangle would be half DC times the height, and once again the halves and the heights divide out, and we're left with AC over DC. So the upshot of all of this is that triangles with a shared height have their areas in the same ratio as their bases. And all we need to say is shared height. The next big idea is similar triangles. Triangles are similar when their angles are equal and their corresponding sides are in proportion. However, with triangles, if the one thing happens, so does the other. For example, what we're saying basically is that if the triangles share the same angles, right, and it's worth noting that they actually only have to have two angles that are the same, the third one will automatically be the same, third angle of triangle. But if they have equal angles, then their corresponding sides will automatically be in proportion. Or if they have their corresponding sides in proportion, then they will be equiangular. So we've got two ways of proving triangles similar, either proving that their angles are equal or proving that their corresponding sides are in proportion. Now, if we've got some similar triangles like we have here, then we can do exactly what we did with the fish. We can, providing we've listed them in the correct order, so we've listed them in the same corresponding order. Notice ACE, we've gone from the 63 degree angle to the 21 to the 96. When we list the other triangle, we must do exactly the same. We must start at the 63 degree angle at D, then go to the 21 at B, and then go to the 96 at P. It doesn't matter which order you list the first one in, but the second one must be in the same corresponding order. Now we can pull a ratio out. So I've taken AC over CE from the small triangle, and that will be, I must take the same corresponding bits from the bigger triangle. So in fact it will be DB over BP. Alternatively, I could take a piece from the small triangle and divide it by the corresponding piece from the bigger triangle. So AE over DP. Now I can take any other piece from the small triangle, maybe AC, and I would divide by the corresponding piece and I will get the same answer. The next big idea with similar triangles has got to do with areas, all right? And when we've got two shapes that are similar, not only triangles, all shapes, then their areas are in a ratio that is equal to the square of the ratio of their sides, right? That's quite a mouthful, but if we look at these two triangles, the side length ratio, if we take two corresponding sides and divide them, we get P divided by M, all right? And that means that the ratio of the areas will be P divided by M squared, or P squared over M squared. Now that maybe doesn't make a lot of sense to you, but let's explore it with rectangles, which are easier to visualize. One of the questions I love to ask people is, how much bigger is the rectangle on the right than the one on the left? Right? And every single person gets it wrong. They all say 3 times. It's not 3 times bigger. It's 3 times bigger in each dimension. That rectangle will actually fit in the big one 3 times along the top, but also 3 times in the height, for a total of 9 times. It's actually 9 times bigger, right? So if shapes are similar, then the ratio of their areas is equal to the square of the ratio of their sides. These two similar rectangles, the small one and the very big one on the right, their sides are in the ratio 1:3. They're definitely similar. Their areas will be in the ratio 1:3 all squared, or 1 squared is to 3 squared, or 1 is to 9. If we just stopped and calculated the areas up front, we would have realized that the one is 9 times bigger than the other. Okay, the next and last idea is the proportional intercept theorem. And what it says is, if a line is drawn parallel to one side of a triangle, then it cuts the other two sides in the same proportion. Proportional intercept theorem, remember when we get the reason, we must specify which lines are parallel. Okay, so for example, if we take the top bit of the line on the left divided by the bottom bit, we'll get the same on the right. Or if we take the whole line on the left divided by the top bit, we must get the same answer if we take the whole line on the right divided by the top bit. Okay, let's just look at that theorem quickly. So in this diagram we can see, since we have a side parallel to one side of a triangle, it cuts the other two sides in the same proportion. Right, those ratios stay the same on either side. If we take corresponding bits and divide them, they stay exactly the same. An important thing with the proportional intercept theorem is that we always have similar triangles. Right? Because of the parallel lines, those two angles are corresponding angles on parallel lines. The blue angle is common, and those two red angles are corresponding angles on parallel lines. So with the proportional intercept theorem, there are always similar triangles at play as well, and that's worth remembering. The converse of the proportional intercept theorem is also true, but it is less common. And what it says, if the sides of a triangle are cut in the same proportion, so for example, if we take the top piece divided by the bottom piece on the left, we get A over P, and if we take the top piece divided by the bottom piece on the right, we get A over P. We get the same ratio. Then the line must be parallel to the third side. Okay, right, next up is strategy. When we indicate ratios of lengths or areas on a diagram, we never use numbers on their own. We use variables to convey a ratio relationship without actually conveying the length. So let's just take a look at this. It says that AB to AC is 2:5, right? That means that piece is like 2 and that piece is like 5, which means that in fact we could let AB be 2 somethings and the balance of the line BC be 3 somethings. Okay, 2G and 3G. We're not saying how long it is, we're merely conveying information about the ratio of the lengths. We also know that BD to DC is 1:3, so if we let BD be 1P, then DC must be 3P. Okay, now we've got a challenge, because the question asks us to determine AB as to DC. We know about AB in terms of G's, but we know about DC in terms of P's. However, there is one space on this diagram, one area on this diagram, one length on this diagram where we can convert G's to P's, where we can exchange the one for the other. The length of BC is 4P, but it's also 3G. So we can solve that to say that P is actually 3/4 of G, right? And if P is 3/4 of G, then DC is 3P, so it's 9/4 of G. And now I've got DC in terms of G, and I've got AB in terms of G. And you'll see that what happens, in fact, if we just do the fraction work in tip and times, the g's will actually divide out and we actually get 8 divided by 9. Okay, we can do something similar with areas. All right, now this is an interesting question, which on the face of it seems absolutely bizarre. What we're asking for is the ratio of this little triangle over here to this triangle over here. Right, and all we are given, in fact, is the ratios of AG to GE. So once again, I'm going to put that in. Now we've got two triangles here, and those two triangles share what? They share a height. You might want to turn the diagram around, but they share a height. Okay, and because of that, their areas are in the ratio 1:3. So we can let the little area at the top, the yellow triangle, have an area of 1A, and the area of the blue triangle have an area of 3A. Now, another thing that comes in, the little triangle at the top is actually similar, that yellow triangle is actually similar to the entire triangle. So if we explore the ratio of the side lengths of the little yellow triangle to the whole triangle, it's actually 1G as to 4G. Now because of that, their areas will be in the ratio 1:4 squared, or 1:16. That tells us that the little yellow triangle is 1A and the entire big triangle is 16A, right? But obviously that means that the white area, in other words, that what we call it a trapezium with the parallel sides, that must be 15A to give us the 16A. But we already have that the little triangle FGE is 3A, so in fact that green triangle must be 12A. Right, now we've got all the bits of this diagram in terms of A, and now the ratio of the area of FGE to FED is just 3A as to 12A. Once again, the A's divide out and we get 1:4. Right, time to try two questions. Pause the video, try them. Okay, so let's first start off and let's fill in the ratio 3 and 5. So 3:5, notice 3 as to the whole line is 5, so 3G, 2G. What we're going to do now, it looks to me like proportional intercept theorem is at play here, but there are two sets of parallel lines. In our mind's eye, we're going to try and shut out the ones that are horizontal, the ones that are going parallel with the ground, okay? And in fact, we're just going to look at the rest of the diagram, okay? So in our mind's eye, we're just shutting that stuff out. Now, it's quite clear that we've got the proportional intercept theorem here. So in fact, we know that AG to GD is also 3:2, so we can put different variables, both 3K and 2K. We're now going to put that bit of diagram back, and now we're going to take out the other parallel lines, right? In our mind's eye, we're just going to say, well, let's just look at that. I'm hoping that you can now clearly see the proportional intercept theorem here, and we know that AD as to DB, the top as to the bottom on the left-hand side, is going to be 3:2 as well. So we can let the top piece be 3P and the bottom piece be 2P. Right, now the question's actually asking us to find the top bit divided by the bottom bit, AG to DB. Just like we had earlier, the challenge is that we know the top bit in terms of K and the bottom bit in terms of P. But there is an area on this line, and it's actually at AD, on this diagram rather, where we have the length of a line, AG, both in terms of P and in terms of K. So we know that 3P is the same as 5K, so P is the same as 5/3 of K, which means that BD is 2 lots of P, it's 10/3 of K. And now I've got both lines in terms of K, and when I do the tip and times thing, and the K's divide out, I get a final answer as 9:10. Right, the very last question is this one. It says BC is a tangent. Find BC if we're given those lengths. So let's put those lengths on. All right, now we haven't got much to play with here. It definitely doesn't look like proportional intercept theorem, right? Those triangles do share a common height, but that's not necessarily going to be useful because this is not about areas. And in fact, there are similar triangles here. If we look at the two triangles, this one here and this one here, right, they don't look similar. But in fact, if we look at this triangle and the big triangle, they certainly look similar, right? So let's try and prove them similar. B1 is equal to A, tan chord. Angle C is common, And so the third angle in the yellow triangle, which is BDC, must be the third angle in the big triangle ABC. So those triangles are similar. Because they're similar, we can pull out ratios. Now we were asked to find BC. So let's take BC out of the left-hand triangle. And if we do that, then we must take AC out of the right-hand triangle. If we take DC out of the left-hand triangle, then we end up with another BC out of the right-hand triangle. All right, so now we've got a reason why we can pull that ratio out. Don't forget the reasons, right? Those triangles are similar, that's why we can extract the ratio. And now if we cross multiply to clear the fractions out, we get BC squared as AC times DC. We know AC, it's the whole length, 18. We know DC is 10, and there's the final answer. All right, we really hope you found this useful, and all the best. Enjoy the rest of your day. Thank you.